Kernel learning based on fast food representation. So we know that kernel method suffers from a scalability problem. The main reason is that we need to store the whole kernel matrix. And the matrix size is m squared, where m is the number of data points. Sometimes we may even need to do some computation on this kernel matrix, such as the inversion, and the computational complexity is even higher. It can be m cubed. And there are all kinds of methods to approximate this kernel matrix, such as the Nystrom algorithm. The Nystrom algorithm takes some part of the kernel matrix to approximate the whole kernel matrix. And also for random kitchen sinks, expand the kernel to get the basis function. And the Fastfood is a further step based on the random kitchen sinks. So in random kitchen sinks, computing the basis function requires n times d complexity, where n is the number of basis functions, d is the dimension of the data. Fastfood approximates the Gaussian matrix, and the computational count is n times log d. So all the above approximation methods, they're based on a given kernel, which means that if we know that this is the best kernel, we can do the approximation, and then we can do the training and prediction. But in kernel methods, one of the main steps is to pick the right kernel. And there are several ways to do it. For example, in support vector machine, we use cross-validation to pick the right bandwidth of the RPF kernel. And there are even more sophisticated kernel selection method called multiple kernel selection. For example, we can explore the space of addition of the kernels. However, all those methods, they're computationally expensive. And this becomes even more computationally expensive when we have a large amount of data set. So the objective of our project is to learn the kernel when we have a large amount of data set. So we combine the previous two problems. So this is how we do it. We use the kernel approximation while we learn the kernel. And this is the basics of the Fastfood. So basically, Fastfood take a Fourier transform of the kernel, and here's k is the kernel function, and then takes a Fourier transform, and we get a spectrum function rho omega. You can regard rho omega as a probability distribution of the probability distribution. Then you can sample the spectrum from this probability distribution, and then you can get the basis function. And here, this is the approximation of the kernel. We have the kernel, which is equal to the inner product of the basis function. And you can simply ignore the complicated matrix operation there. You can simply focus on the S. And basically, this is one term we need to manipulate later. And S is the radius of a multivariate Gaussian matrix, multivariate Gaussian random vector. As I have mentioned, Fastfood decomposes the kernel into basis function in n log t time. And this is based on a given kernel, which means given the spectrum function. We can do the approximation. So in kernel selection, we want to ask the question, which is the best kernel? Which means that which is the best spectrum function? And also which is the best spectrum points? So in order to learn the kernel, we can learn either the spectrum function or the spectrum sample points. We first focus on the spectrum sample points. Given the spectrum sample points, we can recover the kernel matrix like this. K is the kernel matrix, and the first part is the basis function matrix. And basically, this means that kernel matrix is the inner product of this basis function matrix times P times the transpose of the basis function matrix. And here P is a parameter I introduced. So the kernel matrix now is a function of the sample points and the scale of the sample points. So in order to learn the kernel function, kernel matrix, we need to learn this sample point, the scale. So we have two choices, either to learn the spectrum points or to learn the scale. We first focus on learning the scale. And here we make use of the Gaussian process framework. We focus on the regression problem. Recall that for Gaussian process regression, we have the marginal likelihood shown here. And here the K is a matrix. It is the addition of the kernel matrix plus the noise. So in order to learn the kernel, we optimize this marginal likelihood objective function over either the scale or the spectrum points. But here we have an additional term, which is the regularization term. For learning the scale, we introduce the square norm, and this is one formulation. Learning the scale, we fix the spectrum points and then optimize over the scale. We can either learn the spectrum points directly. The only difference is that we have a different regularization term here. We put a prior over the spectrum points. We assume that this spectrum points is a sample from a multivariate Gaussian random vector, and then we set the regularization term as the log probability of all those sample points. So this is two formulations. And here are some preliminary experiments on the previous two methods. And this experiment is based on this very interesting data set, the carbon dioxide density data set. And here the x-axis is the month, and the y-axis is the density of the carbon dioxide. We see that this data has two trends. One is the long-term growing trend, which means that the carbon dioxide density in the air grows as time grows. And it also has a periodic pattern. This pattern means that the carbon dioxide density changes as season changes. So we want to use the kernel to recover these two patterns. For traditional RBF kernel, it can only recover one pattern, which is a long-term growing trend. It cannot recover the periodic change. But our method can recover both change. Here, the blue line is the training part. The green line is the real data set, real test point. And the black one is a prediction with our method. And the red one is the RBF kernel. So although there are some error at the end, our method basically recovers both patterns, the long-term growing trend and the periodical change. And this is the spectrum of the density of the kernel we just learned. We see there are two main components. The first component is near zero, and this component means the long-term trend. And the components near 0.5 is the periodical change. But however, when I try these two methods on real data set, it fails miserably. And here is the result on 9 data set. This column is the result, the result is in terms of the IMSE. And this column is the result of the RBF kernel. This is the ARD, automatic relevant determination. And this is Fastfood. This is basically a sample from the previous two, sample from this one. And this is optimized over the spectrum. This is optimized over the weight. We see that it fails most of the time. At times when this method is better than the RBF kernel, it improves marginally. But the log likely value, likelihood value for those two methods is lower than this one, which means that it suffers from the overfitting problem very strongly. And this is on a very small data set. I don't know whether this method will fail on large data set as well. I don't know. I haven't tried it. So the previous part is basically focused on learning the spectrum points. The other method is to learn the function directly. And here we use a mixture of Gaussians to approximate the real spectrum function. And we assume that the real spectrum function is a mixture of Gaussians. And then we can similarly write out the basis function, write out the kernel matrix in a similar way. And here's the test result. The same 9 data set. And this Gaussian kernel performs better than previous method in 6 data set out of 9. This is the RPF kernel, this is the ARD, this is the new method. This, to some extent, it shows the advantage of this new method. But all previous formulations, they're still based on the kernels, which means that computational complexity is still very high. Now that we already use the Fastfood, we already have the basis function, so we can directly do the prediction based on the basis function. And here we use the Bayesian regression. This Bayesian regression is equivalent to kernel method, except that we have a dual, it's equivalent to Gaussian process. This is basically a dual representation of the Gaussian process. But the computational complexity is much lower, and the computational complexity for this Bayesian regression is n squared times m. Here n is the number of basis functions, m is the data point. But for original kernel method, the computational complexity is m cubed. Now, for this Bayesian regression, the computational complexity scales linearly with the number of data points. And we can try this Bayesian regression on some very large data sets. But unfortunately, the experiment is not finished yet. Hopefully, I can finish before the final report. So this is our project. Thank you.
It's nice that you move on from your midterm report and try to do something new, which is to learn the spectrum function.
Yeah.
Yeah. I'm glad to see that the results get better.
Yeah.
But still, I have this question about the two trains plot.
Okay.
So it appears to me that you are using too large like a bandwidth for the RBF kernel when you do this red plot, so that it only captures the low dimensional, the low frequency changes, but not the high frequency. If you use
you mean you use a wide spectrum function so that you can recover both?
Just RBF kernel. If you use RBF kernel and tune the parameter.
So this is for this RBF kernel result, I learned the parameter, not the parameter I picked myself.
Oh, so this red line.
Yeah. The parameter is also learned by minimizing the minus log likelihood function.
Okay, a cross-validation or something?
No, because in the Gaussian process framework, you already have the parameter in the kernel matrix itself, so you can minimize the minus log likelihood function.
You have control over which kernel you use. You use RBF kernel, but RBF kernel has a parameter.
Yeah, I use RBF kernel. I can only control the initialization.
Do you have any intuition why you choose the spectrum as instead of Gaussian?
Yes.
For example, if you have RBF kernel, I can think of you don't want to use high frequencies, right? So you have something like Gaussian distribution for the frequencies, so you penalize higher frequencies. But
Yeah.
I'm saying it's a mixture of Gaussians.
Yeah, I think RBF kernel is one special case of this mixture of Gaussians.
It's definitely, do you have an intuition of why, you choose certain frequencies somewhere in...
So this is example, right? So for this example, we have made two components. First component near the 0, and then component near 0.5. For this example, the RBF kernel cannot represent this complex spectrum form.
So you even regulate the way you choose your mixture of Gaussians? Because powerful,
the position of the mixture of Gaussian
distributions with your mixture of Gaussians by using suppose I use infinite number of...
It turns out that In real experiments, many of the mixture Gaussian centers are 0. But for some, it can have some component not in 0.
So the part I don't understand is for the eigenfunctions at you are later simulating the eigenfunctions by mixtures of Gaussians. So if you go forward.
Okay.
Yeah,
Yeah.
And you're ensuring that these guys are orthogonal?
Yes.
This is like one D mixture. It's only a spectrum of the kernel information. Okay. And it has nothing.
Then it is just one.
It also has like the spherical. It's still the same kernel extension. It's just instead of drawing the spectrum from some fixed distribution, they now try to draw it from a mixture of function, and they want to learn this spectrum function. So make it adaptive to the problem.
So we do know.
But by spectrum function you mean something that calibrates the eigenvalues or the
So-
eigenfunctions?
Eigenvalues.
Okay, because
So to learn this rho omega here, we do know which the most accurate rho omega. We use the mixture of Gaussian to approximate this function.
You see, this is the eigenfunction decomposition. This
Yeah.
rho.
No, I was thinking that he's trying to simulate the eigenfunctions or the eigenvalues, which is where orthogonality becomes a concern again.
So for mixture of Gaussians, we choose the number of components by cross validation.
And for this result, I picked manually. I pick 3 components here. Yeah, we can use cross-validation to pick the.
But like the number of like parameters you have to cross validate is becoming larger. It's like a harder problem now. Because you have to keep optimizing this.
Well, it depends. We can have a large number of components and have some sparsity constraints. Then, yeah.
Are you also plotting runtimes in your final report for these?
Uh,
Because starting motivation was scalability and speed.
yeah. I'm still running it's on some large data set. Yeah.
Something that is not reported in published papers, but you can report in your project report is the total amount of time it took you to generate one number in this for each of the 3 methods. Because when people do cross-validation, that costs time, but people then show the running time only for the best choice of parameters. But in reality, that is time that does get spent, but nobody reports it, unfortunately.
Okay.
Which is basically also Shashank is raising, that's a very important point actually for practically using these things.
Yeah. Okay, thank you.
Okay.